Thank you very much. This is a tough act to follow, and very happy to speak here. Such a distinguished audience and at such an event with so much positive energy. So I want to tell you a bit about how science is changing in quite dramatic ways, and how machine learning and the next generation of AI systems are going to play a role in that. So let me first rewind around 40 years. So, or actually this picture is from 30 years ago. This is a picture when Garry Kasparov lost against Deep Blue. So this was a major event in the history of AI. People felt for a long time that once computers can beat humans or human world champions in chess, we will have realized artificial intelligence. Unfortunately, as you can see in this picture, the paradox thing in this picture is that it actually looks like Garry Kasparov is not playing against a computer, but against another human. And the reason for this is that, of course, the computers at that time, while they were able to beat a world champion in chess, they couldn't recognize, let alone move chess pieces. So there had to be a human moving these chess pieces. And that's a nice example of what came to be known as Moravec's paradox. So the paradox was things that looked very complicated, that looked like they are a real AI and a human-level intelligence, were surprisingly simple, such as chess, and things that looked very simple, such as recognizing a chess piece, were surprisingly hard. So we all know this has changed through machine learning, and now we think we can do everything just with this data-driven paradigm and scaling up things. And I'm going to tell you that this is not always true, and this has big consequences, especially when it comes to AI for science, where it's not just about maximizing profit, but conveying understanding and understanding systems, coming up with hypotheses, etc. So this is a picture from a paper that was recently published. And this paper was commenting on another work that had trained the neural network to recognize a pneumothorax. So if you have a pneumothorax, you go to hospital, one of the wings of the lung, or maybe even both, collapse. And the system was trained on a population of such patients and recognized pneumothoraces very well. Then they tried to field the system and apply it to new incoming patients, and it completely collapsed. Now, to understand what had happened, they analyzed where the neural network was actually looking when it was taking these decisions. And I don't know if you can see it, but it was looking in particular at a little area around here. On the top left image, there's a little area which shows a tube that gets inserted into the lung in order to let the liquid flow out. Now, unfortunately, the new patients coming in didn't have this tube yet. The tube is put in by doctors once they know that someone has a pneumothorax. New patients didn't have it, it didn't work. So the problem was really that they were looking at something that's correlated with having a pneumothorax in a certain population, but this correlation was not causal, and it completely broke down for new patients coming in. This is what's called a spurious correlation. Now, we think language models can do everything. They are amazing, I agree, but they also fall for spurious correlations. And I'll show you one example. One type of example. This is an optical illusion that many of you may have seen. It's the Ebbinghaus illusion. So if you look at the two orange disks, they look as if they have different size, but in fact they're the same size. Now imagine you're a language model and you're trained on internet data, maybe some images like this, along with some textual explanation. Now you might infer different things about this. So you see this image, someone tells you that two orange disks have the same size. You might conclude, for instance, whenever there's two disks that are orange and that are surrounded by blue disks, they are the same size. That would be a pretty stupid conclusion, wouldn't it? But exactly that's what's happening with language models. So in this example, we take a modern language model. We ask which orange circle is bigger. It says, and the boldface comes from the language model, both orange circles are actually the same size. And this was first found by some PhD students of mine, and it got me down this rabbit hole of trying out my favorite optical illusions with language models, and it falls for all of them. So these are a few optical illusions that you may have seen. So the blue one is the Müller-Lyer illusion, so the two line segments are the same length. And in the bottom left is the Zöllner illusion. These lines are parallel, etc. I think you've probably all seen those illusions. And if we feed them in, but we feed them in extreme versions. So here we're going to ask which of the two line segments is longer. Then again, the model says, immediately recognizes this must be an illusion and concludes that they're the same length. And it works for all of these different examples. So this one also, it's steadfast in claiming that these lines are parallel. Now this is okay, this kind of behavior, as long as there's no change between training and test population, which, if you're a large company training on customer data, you can often ensure that this is the case, if you have enough money to collect data, to let data be labeled, etc. Now, interestingly, if you're in a business of scientific discovery, it's actually sometimes interesting to explicitly model these kind of correlations or to use these correlations, and that's exactly what we've done in this example, which is one of my favorite applications. I very much like astronomy. So this is an application on data collected by the Kepler Space Telescope. And this telescope was staring most of the time at the same patch of the Milky Way from our solar system, looking for what's called exoplanet transits. Now, exoplanet transit means that there's a planet orbiting some other star that passes through the line of sight between that star and us periodically, and this passing through the line of sight leads to a little dip in the brightness as we perceive it from here, or as we perceive it from space, ideally. And we're looking for these little dips, and that's what Kepler was built for, the Space Telescope. Now, if we look at the data from the Kepler Space Telescope, we can see these light curves, and each of these curves in the bottom left is a light curve over 3 months. So the brightness of some star over 3 months. And all these light curves actually belong to the same star, so the light is a little bit smeared out over a few pixels. And what's interesting now is, well, if we think about where does this come from, this information, of course it comes from the star, but it also comes from our instrument. So depending how we measure it, that will influence what we measure. And interestingly, if we look at another star, and the Kepler Space Telescope observed hundreds of thousands of stars at the same time, it turns out the light curves look surprisingly similar sometimes, which is surprising because the stars are light years apart. They don't exchange information. How can these light curves look similar? They can only look similar because the two stars are measured with the same instrument. Now, the effect of the instrument is exactly what we're not interested in as scientists. We want to understand the astrophysical signal. So we want to remove this effect of the instrument, and this is what we can do if we write down this kind of causal model, this model with the arrows. It's a causal model that explains how the data are formed, and we basically came up with an algorithm to explain the data that we are looking at the time in terms of other data of which we know there's no causal connection, or to which there's no causal connection. And if we do that, we can remove the parts that are explained by the other stars. So this is called explaining away in machine learning. We can explain away this spurious correlation, and we did that, and at the time, so we came up with a list of planet candidates, around 20 or 30, and quite a few of them were confirmed afterwards with other measurements. And one of them was especially interesting because it was orbiting its host star in this Goldilocks zone, in the zone where liquid water is possible in terms of the temperature. So this is called the habitable zone. And it became interesting a few years later. I got this text message from my astronomy collaborator from New York. He said, so there was a planet that was on the news. I didn't make the connection, but then he texted me and said, well, this was actually one of our planets. So the planet became famous because it was the first habitable zone exoplanet on which water was found spectroscopically. And that was very nice news, and it continued to get even more interesting. Astronomers then came up with this notion of what they called a Haitian planet, where Haitian is composed of hydrogen and ocean. So these are believed to be planets that are surrounded completely by an ocean, and which is then covered by a hydrogen atmosphere, which is already just the idea of it, this planet covered by an ocean completely, I find mind-blowing. And then, yet again, a few years later, scientists found on the same planet, K2-18b, found carbon dioxide and methane in the atmosphere, which is very interesting because it also occurs here on Earth. It's not a proof, it wasn't a proof for life, but it was certainly consistent and very interesting that this was found there. And then only this year, the planet was in the news again. And it's a very controversial planet now, so I have to be careful. There might be astronomers in the room. I don't want to just take sides in this discussion. So what people believe to have found, some astronomers claim to have found dimethyl sulfide and related compounds, which on Earth are generated by plankton. Now, methodologically, this is a very difficult topic. It's very difficult to infer the composition of an atmosphere given these measurements, spectroscopic measurements taken more than 100 light years away. So it's very difficult, but at the same time extremely exciting. And although this is almost certainly not proof of life anywhere, I think it's quite possible that within the next 10, maybe 20, maybe even less than 10 years, we will find compelling evidence for life elsewhere in the universe. We have also worked on direct exoplanet imaging. So this was transit imaging. We're looking just at the dip in the brightness of the host star in direct imaging, which is only possible for stars that are closer to us. We try to block the light of the star and see the little light of the planet nearby. And we've basically used the same method, which we call half-sibling regression, to, in this case, to explain away certain so-called speckles, certain patterns in the image, explain them away in a way that preserves the planet signal. And doing this, we haven't found anything new yet, but we have been able to find something in data taken before the object was known. And we've made some predictions for the future. And there's observations currently going on in large telescopes, trying to find what we have predicted. So that's very fascinating to be able to contribute to this. I want to move to another astronomical application, which is just as fascinating, or maybe from a fundamental physics point of view, even more fascinating, and that's gravitational wave inference. Now, gravitational waves are emitted whenever masses are accelerated, and they're detectable whenever the masses accelerated are huge and the accelerations are strong. And the video that you just saw was a video how the first ever detected gravitational events would have looked like if you had been able to watch it from nearby. So you saw these black things, they don't emit light, and they merge into one bigger black thing together. Now it's a fascinating problem, and the way this is measured on Earth is using these gravitational wave observatories. These are big physical apparatuses that measure the distortion of space itself over a distance of kilometers. And they get these curves that you see on the right-hand side. These are length distortions that are measured as the gravitational wave passes through Earth. It passes through anything. It doesn't matter if something is opaque or not. It's not light. It's a gravitational wave, and these were measured. So the first such event was measured even before the instrument was officially measuring. It was during some kind of preparation run. The event was so loud that it could have been measured no matter where it occurs in the universe. And now the interesting thing from a machine learning point of view is now we understand reasonably well the forward model. By this I mean, given certain physical parameters of a system that we want to measure, how would the curves look like? But we're interested in the opposite. Given the curves, we want to understand what are the physical parameters, what are the masses of the two black holes, where in the sky were they, etc. And we can train neural networks on this kind of thing to learn this background mapping. And we've recently generalized this to an even more exciting setup, and that's the case of binary neutron star mergers. So neutron stars are, you might have heard of them, they are absolutely fascinating. A neutron star is the heaviest thing you can imagine other than black holes. So if you condense matter as much as you can, then basically the whole planet becomes like the nucleus of one giant atom. And it's then called a neutron star. And if two neutron stars merge into each other, they can form a bigger neutron star temporarily, or they might form a black hole. And this kind of event, as you've just seen a video for simulation, so this kind of event is called a kilonova. And this, you might think this is something that happens out in space. I'm glad I don't have anything to do with it. It turns out that, for instance, most of the gold here on Earth, most of the platinum, palladium, uranium, is probably generated during such kilonova events. So these kilonovas are important for everything that we know and see. And what's interesting about them is now that where black hole mergers are invisible in light, so it doesn't make sense, it doesn't help us much to know where they are. There's no point in pointing a telescope there. This is not the case for binary neutron star mergers. So these neutron stars, they do emit light, and if we can detect very fast where they merge, we can point optical telescopes. And this has been done once, basically by coincidence, but now we have a method, it was just published in Nature a few weeks ago. We have a method that can detect this very fast in the future, probably within seconds. So this is a very exciting field, gravitational wave physics. It's potentially even able to look back into the past much further than light astronomy, because as you probably know, the universe at the beginning was opaque. No light could go through, so we cannot look until the very beginning. But the universe is never opaque for gravitational waves. So I want to show you a few more nice images from other applications. Now, one other aspect that I like about AI-driven discovery is that it gives you means of crowdsourcing parts of the scientific process. And this is one such example. So this is, if you do an image search for NGC 5907, that's a name of a galaxy, you get lots of images like shown on the screen. These are mostly images taken by amateur astronomers. And the professionals, they sometimes they refer to these images as pretty pictures, suggesting that they look nice, but they're not useful for doing science with them. But if you have a lot of such images, and if you can make certain assumptions, and we make one specific assumption about the way they have been processed, then you can try to combine them and see if there's scientific information in them. And we built this algorithm that automatically registers them and combines them, and over time then builds this image at the bottom right. And there was a reason why we looked at this specific galaxy. If you look at this image, you see a little, what astronomers call a tidal stream. So you see this stream of stars to the left. So the image that we computed from all these amateur images is the right-hand side one. If you compare it to the deepest professional image at the time, you can see this stream actually does seem to exist. What was slightly puzzling for us was that we only found the bottom half of that string, of that spiral of that stream. But then we couldn't change it. We were trying to process our image to bring out the top one. It just wasn't there. And then a few years later, the astronomers started to argue amongst each other because other astronomers couldn't reproduce the top stream either. So that was interesting. Now, last one. This is not about citizen science. This one is about maybe the aesthetic aspects. I'm quite interested, not just in astronomy in general, but also specifically into solar eclipses. And as you probably know, next year there's a next solar eclipse in Europe, in Spain, in August. I think once in your life, everybody should see a solar eclipse. And the amazing thing, people call it the black sun. And I suspect it's the highest contrast that you can see anywhere in the natural world, this contrast between the black moon in front of this very bright sun, in front of this what's called the corona of the sun. Now, unfortunately, if you take pictures, it never does justice to the things. And we have very good high dynamic range displays nowadays. So we were starting to think about how to better record this kind of data, and we came up with methods of increasing the local contrast by essentially doing a form of image deconvolution, and then you get images like the ones on the right, and we've continued working in this direction, and I think this I wanted to show because I find it also aesthetically very interesting. This is now, if you bring out the very, very faint contrast in this high dynamic range image in the corona, you see all these structures that come from the magnetic field and from the ejections of the sun, etc. Now I want to change gears a little bit and connect this search for truth, that we search for truthful information that is part of the scientific process, to language models, which of course nowadays in the public people almost equate language models and AI. And of course all our students want to work on language models if you're an AI researcher nowadays. So we thought about language models. This is work with Léon Boutou about language models, and was a bit of an experiment, try to compare them to certain elements from the literature, from Borges. And as part of that, we came up with this notion, what we call the perfect language model. So this is an ideal that the existing language models don't reach, but it's interesting to think about it. So you imagine a collection of all sensible texts, anything that makes sense if a human reads it. Now we print a few words on a tape, we call this our prompt. We find all occurrences of these exact words in our collection. The collection is huge, so it will occur many, many times. We randomly pick one of these occurrences, read the next word, print it on the tape, and repeat. Now this is a language model. This will be a very good language model. The interesting thing about this is, of course, it's a completely mechanistic process. It seems there's not much intelligence in the actual algorithm, how this runs. So if there's any intelligence there, it must be in the data set. And really, it's only about fluency and about the narrative. And I find this nice analogy. I once read about this gentleman here. His name is Nigel Richards. He's from New Zealand. He was a world champion in Scrabble multiple times. And I think at some point he must have gotten bored with competing in the Scrabble World Championship, and he decided to compete in the Francophone Scrabble World Championship. But he doesn't speak French. So he took a French dictionary or a Scrabble dictionary, learned it by heart, and lo and behold, became Scrabble World Champion in French. And I believe he still doesn't speak French. So language models are a little bit like this. And the second aspect of language models that I find fascinating is this one. If you think about why language models work as well as they do, it's not because they really have a collection of all possible texts, because there are many texts that you can write that don't exist in this form in the internet. It's just impossible. So the data, as large as it is, the whole internet, it's still a very sparse data set compared to what language models can produce. And the reason why they can produce it is that the set of sensible texts has a very rich structure. The reason is that there are, if you have a few sensible sentences, and in addition you have transformations, such as replacing one word, changing the tense, changing from active to passive, renaming the subject, changing a place, there are billions or millions of transformations that keep this set invariant, as a mathematician would say. So if you can learn these basic structures and the transformations, then you're in business. Unfortunately, if you look at the set of all factual texts, it doesn't have this rich structure. If you take a factual statement and you change one name, it's probably no longer true factually. So this is a big problem for language models, because exactly the method that makes them strong fails them when it comes to produce factual text. So we have to do a lot of extra work to make them say the truth. And of course, that's not a new insight. Maybe it's new for AI. I think it was always clear to newspaper people. This is a comment from the former editor of The Guardian of Manchester. Comment is free, but facts are sacred. And for us, this is very difficult to deal with this kind of intelligence, because we think that fluency and literacy, so if someone is very fluent, very eloquent, we think what they're saying must make sense. Maybe we also think what they're saying must be true. And we have to learn to be careful with these kind of things. So let's take a quick look at the big picture to conclude. So this is a slide that I made when I first attended a conference like this, which was 10 or 15 years ago in New York. So this is a picture from the first industrial revolution, and we know it was triggered by the steam engine, by water power. And the second one then was driven by electrification. So really it was about how to generate and convert forms of energy. And the current change has been called the digital revolution, but really it started already in the mid-20th century. And it was under the name of cybernetics and information theory, and it replaced energy by information. Now, like energy, information can be processed by people manually. And the first computers, as we probably know, were humans, mostly women, doing calculations by hand before we developed mechanical or electronic computers. But information is much more important to the human condition than energy. We're not particularly proud of being good at processing energy, but we think we're very good with information. And the reason why we're dominating this planet amongst all other animals is that we're probably better at information processing, not that we are, as animals, better at energy processing. Now we're probably already in the second phase of this revolution now. At the beginning, it was about computers, algorithms that were programmed by humans that processed information. Now we have methods that can harvest information from large data sets. We have machine learning, etc. We have methods of causal machine learning. So step by step, we're getting better at this, but we still have this problem that it's much closer to what makes us human, and therefore also the use of this might have much bigger implications for us as humans. And I think we're seeing this. Of course, we've always seen manipulation of information, but in the past, manipulation of information was expensive. You had to put a lot of work into it. And nowadays, anyone can do it. And you can use this in all sorts of, and I think there are many experts in the room. I don't need to talk on this. I just want to flag one little thing, one example here. This is a paper from our lab very recently where we tested different language models as agents that had to take sort of moral decisions in different game theoretic settings with different framings. And it was very interesting that the different language models, also depending on where they were developed, for instance, handled these issues of cooperation very differently. So this is never neutral. Technology is always developed in a cultural context. It's culturally contingent, and it's important for us, also important for us in Europe, that our voice is heard in this. And this is the motivation why some of us in the European AI community got together 7 or 8 years ago and started ALICE, started a PhD program, a pan-European PhD program, which now also includes Canada. We consider Canada part of Europe now, and we've started to build up sites, AI sites in Europe, and a research program. So we have a thriving PhD program where we get between 5,000 and 10,000 applications per year. We have these sites that they were self-funded, starting with existing places at universities, but by now also including two actual institutes that are privately funded, and these research programs, and very active. If you look at the webpage, for instance, I copied what's happening now in July, and I showed it because the first entry is a summer school in Lausanne, not far from here. So there's stuff going on all the time. It's extremely attractive for the students, and it's really trying to make Europe competitive, and to make Europe play a role in modern AI. I already mentioned 2 institutes, so I was fortunate to be involved in one of them in Tübingen, and the other one was just recently announced in Finland, and we know of many other places that want to start an institute. So this is really, I think, the most optimistic thing about current European AI core technology. And we're trying to argue that what we really need is something like CERN or EMBL for AI, because these technologies have to be developed here. And also, even in addition to just this sort of functional argument that these technologies should be also developed and understood here, the technologies maybe is the most dramatic change to the human condition. And we have very little real understanding of what these methods do. So from a scientific point of view, no matter which science you work on, I think everybody knows that this is going to be crucial to understand what's going on here. So from my point of view, for my own lab, apart from these applications that I love in the sciences, the topics that I really want to understand, they might look like very different ones, but they're actually the same. Both of it could be called world modeling. So Konrad Lorenz once said, thinking is acting in an imagined space. So we have to learn models that contain this notion of action. So that means causal models, not just correlational models. Now for the scientific applications, the same kind of methodology gives us tools to decompose complex systems into mechanisms and build what we call causal digital twins of system. So now, last slide, with this slightly provocative title, is AI intelligent? It should be intelligent from the title, but I try to explain to you, current AI systems make rather stupid mistakes. The reason is that they're just building on correlations, which is effectively pattern recognition. And if you now, I also told you about causal models. They try to understand the effect of interventions. If we go with Konrad Lorenz, this is now the domain of thinking. And if we go now to Greek mythology, I would argue that the god of pattern recognition is Hermes. So he's the god of trade, the god of cunning, god exploiting dependencies, etc. And the god of thinking must be Athene. Now you might ask yourself, is that the whole story? No, there's also a human in the picture. This is a picture when Perseus gets advice from Athene and Hermes before fighting the Medusa. And even if you understand the effect of interventions, that doesn't relieve you from the burden of choosing interventions. And that's something that humans have to do, and that will continue. That should continue like this, that humans have to take these kind of decisions. So in the end, I think for our future with AI, the crucial question is maybe not so much whether AI is intelligence, but whether we are intelligent in how to use it. Thank you very much.